Welcome to this lecture on Chapter 17, where we're going to talk about geological time, concepts, and principles. So in this lecture, we're going to talk about the concept of geological time and how its measurement has changed throughout human history. So that we're going to compare relative dating to absolute dating. We're going to figure out why this concept has changed and how it's changed throughout human history. We're going to use the principle of uniformitarianism when we do this, so you'll understand how it's a fundamental property of geology or an idea in geology. And then we're going to talk about relative dating and how it transformed our idea of how the world formed, and it helps us place geological events in a sequential order. And it also provides us a way to interpret geological history, which in turn helps us interpret biological history. There are three types of unconformities that we'll run into when we're trying to do our relative dating. It's disconformity, an angular unconformity, and a nonconformity. We're going to discuss how the time equivalency of rock units is demonstrated through various correlation techniques of fossils and different rock layers, and then we're going to use absolute dating techniques using radioactive isotopes to date geological events. So here is a picture of the Grand Canyon, which was explored by Major John Wesley Powell, and that was the mid-1800s, where he led a group of explorers down the Colorado River. There's even a lake named after Major Powell. It's called Lake Powell. And what he noted is the different rock layers, as you can see here, which shows us the principle of original horizontality, which sets up the relative dating schemes that we're going to talk about, and how they actually figure out the age of rocks based upon this idea that something is there, you lay down another layer over the top of it, and you get a sequential order in these layers. And the principle of original horizontality, if you guys remember, was Nicholas Steno, and he was actually from the mid-1600s, I believe. And the principle of original horizontality basically says that layers of sediment are originally deposited horizontally and due to the action of gravity. Geological time is actually an immense contribution to all of the sciences because we use the logic in the relative dating, which is basically reasoning one comes before the other, to interpret biological history as well as other historical sciences to figure out, what came first and how we can reconstruct like paleoecological events and things like that. So how is geological time measured? Well, I think we should go back to some history here. When I talked about Nicholas Steno, he's the one that came up with the idea of original horizontality, but he had not only talked about the layers being laid down in a horizontal manner, he also stated he had a second idea, which that younger rock units were deposited on top of older rock units. And this is sort of like when you lay down paint. You have one layer down, you can paint over the top of it, but that lower layer of paint doesn't go away, and if you were to cut through it, you would find that lower layer of paint. So the oldest layer is always on the bottom. It's the first layer put down in a sense, and the newer layers are laid on top of that. This concept was mulled over by a lot of the geologists of the time, and then an additional concept was proposed by James Hutton, which it says in the book, and this was later emphasized by Charles Lyell, and this was like the early 1800s, late 1700s. And this was the idea that geological processes are uniform, and so it's the idea that anything that's going on today, meaning physics or chemistry or whatever, was going on in the past. And they are uniform in both frequency and the magnitude, so that things don't change dramatically, and we operate under the same physics now as we did in the past. And that was the principle of uniformitarianism. But as these different scientists came together and tried to figure out the different rock layers, they started correlating rock layers across continents, things like that, and they came up with the worldwide time scale of Earth's history. And depending on what methods they used, it gives us better resolution. So in a sense, the relative dating scheme, which is basically comparing fossils and rock layers, was known as this is older than that, and it's a logical sequential order, just like laying down paint. And then we came up with absolute dating methods later on. This is, in the 1900s, where we could use radiometric dating or radioactive isotopes, and we can say this rock is, so many millions of years old, like this rock is 12 million years old, or or however old it is, with a very specific measure based upon the half-life of radioactive isotopes. So basically, we've established this scale, and it helps us. It gives us the framework, or the first stage for studying all of the other sciences, because we can get an idea of how old the Earth is. So we'll start out with talking about relative dating methods. Go back to Nicholas Steno, and where we think about, he was basically the one that came up with this idea of superposition that states that an undisturbed succession of sedimentary layers, the oldest layer is on the bottom. It stems from his original horizontality idea. But this is the law of superposition, and it's an axiom drawn from Nicholas Steno's work. But before we could figure out stuff using radiometric dating, we didn't really have a reliable method for absolute dating, so we used this is older than that based upon correlating different structures. So just observational data, which is what fossil is found where, and it's found in this rock type, and this type is found over this other rock type that has a different kind of fossil in it. But it doesn't tell us how long ago things took place. So that's why we call it relative dating. It's relative to one other layer or one other fossil. And it provided us a means, or geologists a means, to interpret geological history and develop a relative geological time scale, which then of course sets it up really well for when we actually move into radiometric dating. But they formulated basic principles in deciphering the age of the Earth, and of course we've talked about James Hutton, who's the father of modern geology, and he suggested that these present-day processes like floods, with sandy beaches and all this kind of stuff that develop in the present day could explain the geological features in the past. And of course we've talked about the principle of uniformitarianism, and that's basically the idea, is that if we observe layers in a lake and then we dig down into that lake, we can actually count up the layers and get the age of the lake. And now obviously it's not hard to extrapolate from the sandy bottom of the lake to sandstone in layers as well. And so the idea became pretty well entrenched because it was so logical. So of course today this principle holds that the laws of nature have been constant through time, and the physics and the processes behind them haven't changed. And these processes operating today have been operating in the past. And we have some principles of relative dating that we derive from this idea of uniformitarianism, and that's the superposition, which is the one layer on top of another, and the layer that's on the bottom is the oldest. We have the idea of original horizontality, that all layers were laid down horizontally. We have cross-cutting relationships that change the nature of the understanding of that sequential order based upon what we cut through, just like the paint analogy. And then we have lateral continuity, so if you find one rock layer in one area, even though there's some erosion and there's a gap there, you can go to a different area of land and find the same rock layers. They just, in between it, has eroded away. We also have these principles of inclusion, and then of course we're going to talk about fossil succession. So on our picture of Bryce Canyon right here, I'm going to sort of outline what I was just talking about. I'll use blue so you should be able to see it. So we're talking about superposition. The rocks down here, these layers right here, are going to be older than these layers here, that are going to be older than the red layers here, they're going to be older than the white layers there, and they're older than these layers, which are now a little bit darker red, some more light layers, etc. This is probably all sandstone. And we know that if once this was laid down, this is horizontal now, but we know because of the uplift and the movement of the continents can change the pitch of these layers. But in this case, we have superposition, and then we have original horizontality, that these were all laid down in flat layers, obviously. And then we have the cross-cutting relationships, And cross-cutting relationships would be like when we cut through the paint. So if we have an inclusion, well, my pin disappeared. If we have an inclusion, oh, it's there. If we have an inclusion and we were to cut through this inclusion with this blue would be younger than the rocks themselves because it's cutting through the rock, and that's the cross-cutting relationship. So like an igneous intrusion would be younger than the rock that it's cutting through. And then of course we got the lateral continuity, which means it continues in a lateral fashion, that these white layers right here are the same white layers right here, but there's been a bunch of erosion in between right here. Even though the white layers aren't there, we can assume because of the lateral continuity that these white layers here are the same as these white layers here. Now on the very close relationships it's easy to see, but once you get out hundreds of miles, sometimes this gets a little more difficult to identify. Just as long as you know what kind of rocks you're looking at and the age of those rocks, you're pretty good. Or usually we look at fossils when we look at that. And then there's the principle of inclusions, which means they're either young. Well, the inclusions can be older or younger depending on what rock type they're in. So the inclusions are always older than the rock that they're in, and we'll see that when we look at how rocks change over time and erode. And then, of course, we can talk about fossil succession, which is there are certain fossils that are found in older rocks, and they come underneath other layers of rocks, which kind of correlates with that superposition idea, the older rocks that are on the bottom. And if the older rocks contain fossils, those fossils are older than the fossils contained in the younger rocks. And this is a picture from Colorado that I took when I was just out doing research, and it's probably a road cut. And I just wanted to show you if I were to date these rocks using relative dating methods, obviously these would be older than these layers up here. And there are some layers that are very thick, which they contain more sand, and they have these weird inclusions here. But it just means that, there's different, this could have been a stream bed at one point, and there's a bunch of layers that were laid down, and there's different densities of the rocks. But the point is the layers on the bottom are older than the layers on top. And this is the idea that Nicholas Steno presented in the original horizontality and superposition. We discussed lateral continuity when we were looking at the Bryce Canyon picture. I think it's Bryce Canyon, it's in your book. But where you have sediment that extends laterally in all directions, and it might thin out in certain points where it terminates against a different depositional basin, which means that we have these tongues that will come out, and obviously they've eroded away, and they're depositing. Think of this as deposits from a stream or something that extend out so far, and they will only go so far, and then the lake bed will change, or the size of the deposits will change. But ash beds are also like this. When we talk about volcanic lava flows, these are also tongues of, that extend in lateral directions, but they do peter out because, volcanoes don't cover everything. But then you can also have ash beds that are quite broadly distributed, and they will cover all layers. Keep this in mind when we talk about absolute dating, because ash layers are very good for finding radioactive isotopes in, and then comparing them to the daughter nuclei, knowing how old it was based on half-life. We're going to talk about that. Here are the cross-cutting relationships that we talked about. So anything that cuts through the bed, the horizontal bed that was already laid down. So in this case, this right here is, I don't know what this person looks like, they're gathering water, but this intrusion, this igneous intrusion in the other rock, this is shale or something next to it, is younger. So this is younger than the rock it is in. Here, what they're showing you is we have beds that are already laid down, and we have a fault that runs up and down this direction. This fault is younger than the layers that it's cutting through, or cross-cutting. So one question that we run into is, how do we tell the difference between a cross-cutting bed, so an intrusive lava, or an intrusive igneous flow, or a lava flow. And what you can see here, and it's in the book, but here we have a baked zone on one side right here, and there's no baked zone up here on the top, which means this was a lava flow, which means these layers were laid down after the lava flow. Here we have a baked zone on both sides, which means this is going into an area of the rock, probably a fracture, and getting forced in under high pressure, and it's actually younger than the rocks that it's intruding on, right? Because it's included, it's an inclusion now. And the little pieces of rocks that are in the sill here are going to be older than the magma that intruded, because they're breaking off from the older rock. They're included in the lava, and we're going to talk about that in a little bit. We're actually going to talk about it right now in the next slide. So principles of inclusion. So inclusions of rocks are older than the host rock. So in this case, if you look at the pieces of rock that are included, we have magma that is melting the surrounding rock, and we have sandstone right here. And the sandstone's this magma is going to melt up through the rock, and the pieces of sandstone that are included in the magma, these pieces right here, and you'll have a baked zone on the sandstone as well. The sandstone is older than the granite that it's in. Now we also have the reverse case where you have a granite batholith that's already there. You get some erosion and deposition and the sandy bed, and then you get sandstone, and we'll find the granite class included in the sandstone, and these are going to be older than the sandstone. So here we have basalt inclusions right here, little pieces in the granite right here, but since they're inclusions, the inclusions are older than the granite. So granite starts as, think of it as well, it's magma. It's magma that cools. It's granitic magma. But in this case, the basalt was already present, and the granitic magma melted up through the basalt, and pieces of the basalt fell off into the magma that turned into granite. And so these inclusions are older than the granite itself. Then we have the principle of fossil succession. So in the principle of fossil succession, this basically is where we find fossils that look a specific way, and you find them in specific layers. So here we have this sort of clam-shaped fossil, and a trilobite. This is a brachiopod, a trilobite, and this one I'm not quite sure what it is. It's probably a coral of some sort. And they're over here as well, and what you'll note is we only find them in this layer right here, and these layers here. So there's some sandstone and some shale, and it looks like we only find them in the shale over on this side, but we find the same fossils, and so we can correlate all of these layers based upon the types of fossils that we find in them. Same thing with this side, where you have different fossils from different layers, even though the layers even have sandstone in this layer, but you don't actually find these fossils in this sandstone. You find these fossils in this sandstone, so that you know that this sandstone is from a newer, younger age than the sandstone that you would find underneath it, or the fossils underneath it anyway. So the idea is that you have this principle of fossil succession due to evolution, and there's a video of William Smith that you guys, or it's a video from the Open University, where one of the geologists, I think his name was Chris Wilson, if I remember right. Anyway, he was talking about William Smith and how this individual worked on the canals of England, and he noted the fossil assemblages succeeding one another in specific types of rock. And if you watch that video, it's from when we were talking about geological time. It's quite fascinating. When we're correlating the fossils, we also run into these unconformities where the fossils don't really conform to the layers that are there, or the rock layers don't even conform to the layers we expect to be there, based upon this lateral and horizontal deposition. So we have these unconformities, which are these surfaces of discontinuity in the rock, in the sediment deposition of the rock record, and they encompass some pretty large amounts of time. And basically, they result from non-deposition, which means an exposed or an area not covered in water, or somewhere where you get a good depositional environment, or erosion due to the fact of that these are now exposed areas that erode down. So in this case, pen, you have layers that we know are found in other areas, right? So here we have A. They'll get eroded down in a different area, and this hiatus, this time erosion, which is what you see right here, takes away about 3 million years is what it looks like. I'm looking at this over here. There's 3 million years that were lost. It looks like this thing got chopped off and fell down on top of there. It's like you see that in the, you know, in the, I don't know about comics, but you see it when they do animation. But yeah, there's a lost time here, and this is a discontinuity. And there are different types of discontinuities. In this case, this discontinuity is called an unconformity. So it's the amount of rock is removed by erosion. There's a hiatus in the record. Doesn't mean there's a hiatus in deposition. It just means it went away. And then we get an unconformity of, in this case, 3 million years, which is a pause or a lost amount of time interval in the geological record. There are different kinds of disconformities too, and these separate younger and older sedimentary strata that are parallel to each other. So a disconformity separates younger from older sedimentary rock. It's one type of unconformity. It's called a disconformity. Then you have an angular unconformity, which is an erosional surface that is tilted and then, or overfolded rocks, and then there's more deposition. And then you have a nonconformity, which is it doesn't conform at all because there's an igneous intrusion or metamorphic section of the rock that's overlaid by younger rock that's either deposited or was not melted, in a sense, usually a depositional or erosional surface as well. So if you look, we have this in Michigan. We have the Jurassic rocks in some parts of Michigan, and we have the Mississippian rocks as well. This is actually not in Mississippi, though. I think this is down in Kentucky. But you have an area that, in this case, is, you know, we get a depositional environment. You have these layers. Here are the layers right here that are laid down. You get erosional uplift and erosion, which means this layer right here, which is, I don't know if that doesn't look like a shale. It's a different kind of rock. I don't know what the symbol is for that rock. Gets eroded away, right there, and then you get more deposition. There's a green sandstone, and then this rock layer that's a shale right there. And then because you have more deposition, you have the Jurassic rocks right here, and then the Mississippian rocks underneath that, which is a disconformity. An angular unconformity is the same idea in the sense that you are getting a gap in the record, but often the gap it's kind of weird because how far are the angles and what was lost. You don't know if this is actually going like this, and so you actually have eroded away some surface that you actually no longer find. But the angular unconformity is where you tilt the rock layers due to uplift, and you end up with an angle, and then you get more erosion, and then you get another layer that's laid down, and the younger rocks are deposited on that. And this is what it looks like. It's basically when you have the original deposition with the different rock layers right here, that there's uplift and tilting, sort of like the Rocky Mountains, and the layers are tilted at the side, so the same rock layers are now going down like this. You get erosion on the surface. You get another layer laid down, and then the lake goes away or whatever was there. You get more erosion, and you end up with that. This is the picture of those famous rocks that the other geologist Chris Bell was talking about from Open University. He actually reads from Hutton's diary, I think, or scientific log book. And a nonconformity is where you get an erosional surface that basically is either melted or changed due to igneous activity. So we have the nonconformity is right here, and it's melted this area. And this is how that happens. You have an intrusion of magma, uplift and erosion. You get and it basically gets rid of whatever was on top, and you get more uplift and erosion, but you get deposition of new layers. This is actually one of the more difficult ones to figure out what was going on, because, and this is the Grand Canyon, where you have sedimentary rocks from the Paleozoic and the Precambrian rocks, so this would be the Vishnu schist and whatever's on top of that. Now if we were to apply all of these different dates, and it's in the book, you'll note that you can start at the bottom or the top. Some students like to start at the bottom, some like to start at the top. I like to start at the top because you can move down. If you start at the bottom, often you don't know where to start because of the angular unconformities. But in this case, A is the oldest, right? That's the first one laid down. B is laid down next. D is the next layer here. And then we get E, which is over here. And then F is laid down. And then G. And then we have a layer of J. There's an unconformity right here. And then J is laid down, and then K is next. We have L, we have another unconformity, and P is here, and then you have Q. Now S is a lava flow, so it's in the igneous section here, but that would be on top of Q. And then of course you have T, which is the oldest right there. You also have these inclusions, which came after those, is R is the youngest up until it's an inclusion here because it has a bake zone on all sides, right? Then you have M, which R is included in, or goes through M, so M had to be there in order for R to melt, and that's how you put the igneous rocks. You can actually stack these so that they're included all the way across. But if you follow the principles of relative dating, you can reconstruct the entire geological history of an area based upon these different layers. And in those layers I just showed you, this is basically what we have going on. So you can reconstruct it based upon how they start. So we have the sedimentary deposition, which is the A, B, C, D, E, F, G in the previous slide. You get uplift, there's a fault, which we didn't talk about, that's H. Then there's more erosion, you get more deposition right here, which is these unconformities. And then you get more sediment deposition, and you get this intrusion, this igneous intrusion, I think it was M. Yeah, it is M, it's right there, M. And then you have uplift and erosion, which erodes off the top here. You get more deposition in sedimentary layers. And then you have R, which is igneous intrusion and all the other stuff. Then Q is laid down. Actually, Q doesn't come next. Yeah, Q was laid down first because of the way they have the baking zone, so it looks kind of weird. So Q actually came before R in the slide previously. And then S is the last layer here, right before T. And so if you follow just the letters, you should be able to figure out or reconstruct any geological region based upon past events. Then we move into correlating rock layers using fossils. So correlation is basically a method for demonstrating the equivalency of rock units from one area to another. So we have this lateral continuity, and we have to make sure that this lateral continuity holds, and it usually holds for the fossils. So there's a time equivalence here, which is demonstrated by the same fossils occurring in a specific area. There are guide fossils or index fossils. We call them index fossils. I think they call them guide fossils in Britain. But for us, we have here we have, looks like Lingula, Atropa, and Paradoxides. And if you notice, they have these lines. These lines denote how long we find them in the fossil record based upon just the relative dating scheme. And if you notice for this one, it's found all the way through till today. It changes. Now, don't get me wrong. They don't look exactly the same. They're related, but there's an unbroken lineage of fossils stepwise all the way through the fossil record, all the way till the present with Lingula, and we have Atropa and Paradoxides, which overlap. Now there is a fossil gap right here if you only find these fossils right here at the end of the Cambrian. So you wouldn't be able, if you found rock and you didn't find any fossils there, you would be hard pressed to date it if you didn't have. There's some other fossils you can find as well. It's not just the fossils that we're showing here. These are just good index fossils. Some live for a brief period of time, some live for a long period of time. If you look at how we correlate them overall, this is how we correlate. We have all the different fossils, we know when they overlap, and we can limit ourselves based upon the different kinds of fossils that we find to a specific zone or date, age, relative age. And here we have, looks like shale, and this is a limestone right there. And even though they are different rock types, we find the same fossils, which means they're correlated. There are concurrent range zones, which I have in the notes, that all these fossils overlap. And using those techniques, we can reconstruct all the different layers going all the way back to the Precambrian, that's older than 542 million years, to pretty much the present. Here we have the Wasatch Formation, which is the Paleogene, goes all the way through the Cretaceous. And this is all found in Zion National Park, Utah, Bryce Canyon, which is the one we already saw. It was Bryce Canyon we were looking at, and then Grand Canyon, which goes down through Arizona. And that's because the elevation drops due to uplift and the movement of the Colorado River cutting through all these different layers. We can reconstruct all the different levels, and one builds on top of the other. So what you look here, what you want to note is you have layers in these specific areas that are on top of each other, but there are gaps, like this lateral continuity that we talked about. So here's the Kaibab limestone that crosses right here. Here's the Navajo sandstone. We can correlate these layers, and so that we can continue our climb through the geological history by looking at the different rock layers and then correlating different regions of the country or land surface using lateral continuity. As we move into the new dating that we use today, we use subsurface correlation, which means we now can drill down and we can correlate specific rocks based upon the returning either resistivity, radioactivity logs, and seismic profiles. So in this case, they're showing you a seismic profile, which is where they send down a shock wave or something, and they record all of the reflections in the densities of the rocks as it reflects back. And then you have the resistivity or radioactivity. This is radioactivity, actually. There's a log which shows you that the seismic profiles and the radioactivity of known rocks respond in a very similar manner, and you can actually reconstruct the types of rocks when you drill down through a core. It's actually how we find oil in most cases, by doing this kind of correlation. But when we drill for oil, we're also correlating rock layers because we're looking for specific ages of rocks so that we can find the oil, or actually we're looking for coral reefs. That's what we're really looking for. We're looking for the tongue of a reef so we can find where the oil would be deposited or captured. Which moves us directly into absolute dating. And there's different kinds of radioactive decay that we use in absolute dating, and I'm going to go through them right now. So we have alpha decay, which is where you lose a helium nucleus, which means that the parent nucleus loses an alpha particle, which is 2 protons and 2 neutrons. And you have a new daughter nucleus, which is a different element because you now change the atomic number by -2 because you've lost 2 protons, but you've changed the mass by -4 because you lost 2 neutrons as well. So that the new daughter nucleus may or may not be stable, but you've lost basically a helium nucleus when you've done that. And it changes the atomic number and the atomic mass. And we have Marie and Pierre Curie, that the ones that were looking at radioactivity. They discovered it in the late 19th century. And soon after that, geologists started using radioactive isotopes and radioactive isotope decay to determine how old rocks were to a very specific time period or time. The next absolute dating method they use is a beta particle decay, and we're going to talk about the decay series in a second, but this is where we actually change a neutron into a proton and give off an electron, which is the beta particle, which means we increase the atomic number of an element by 1 because you're adding a proton, but the atomic mass does not change because you're changing a neutron into a proton, and they are the same mass. I'm going to talk about another dating method or another type of decay called electron capture, which is the reverse of the beta decay. But here we have using just alpha and beta decay, which is, it's shown on, this is from your book, so you can follow along in your book. But so we start out with uranium-238, which is found all over in Michigan, by the way, in the clays, and it will go through an alpha decay, which means it's losing 2 protons, and so its atomic number drops by 2, and its mass is dropping by 4, 238 to 234. And then you go through a beta decay, which adds the atomic number by 1, but doesn't change the mass. So we have protactinium, which is 234, and it was thorium-234 that we started with. Then we go through another beta decay step. This is uranium-234. This is the uranium they want to use in breeder reactors. We can talk about that. I probably won't, but it's another type of radioactive or nuclear energy that's actually quite clean in a sense. We don't use it though because we're afraid of nuclear reactions for whatever reason. Okay, and we go through another alpha decay, which means we lose 4 out of our mass and 2 out of our atomic number, etc. So we make thorium-230 rather than thorium-234, which means we have basically the same number of protons, different numbers of neutrons, which is why they're unstable. Then we go through another alpha decay. This is radon. This is the stuff that we're worried about in our house, so because it'll break down and into polonium, which is quite toxic, radioactive. This is, I don't know if you remember when there was this big, national intrigue or international intrigue where a spy that had gone to England, I think, was killed by the KGB when they're not the KGB anymore. But, it's real sort of James Bond kind of stuff. But they used polonium and they poisoned him in his food somewhere in England. But anyway, and then that will decay to lead-214, which then will go through a beta decay, which means you're changing the atomic number, but you're changing the atomic number, but not the atomic mass. That's what I was trying to say. And the same kind of thing, you're changing the atomic number, but not the atomic mass. So you go to another polonium, and then you go through another alpha decay, which has more lead. You go to bismuth, which is another beta decay. Polonium, again, same mass, different number of protons. Go through another beta decay. So there are 3 types of polonium here, which are toxic, and then of course the lead-206 that we are a little more stable. So it's kind of interesting because all the lead that we have still is radioactive. Like when you handle lead, and there's, it still is going through radioactive decay. It's just very small amounts. Then, of course, like I said, there's the reverse of radioactive or beta decay, and that's electron capture, which is where this electron here, it's like the reverse. It's a high-energy electron. Think of a gamma ray in a sense, but it's a high-energy electron. It's not a gamma ray. It's a high-energy electron that comes in and hits a proton. It doesn't change the mass, but it changes that proton into a neutron. So you actually change the atomic number to a -1, means you're subtracting 1, but the mass does not change because changing from a proton to a neutron, they are the same mass. But here are all the different decay series. Here are the decays. You have the alpha particle, which again is just a helium nucleus. You have a beta particle, which is an electron that leaves due to the conversion of a neutron to a proton, and then the reverse is the electron capture, where you capture an electron and convert a proton to a neutron. I'm going to skip over these rapidly because it's the same thing that I just talked about. So this is alpha decay, beta decay, and electron capture. And we know that these radioactive isotopes decay in a very clock-like manner because it's a probability of decay, and that probability is clock-like. And in this case, we know that they're using the analogy of water dripping in a glass from a leaky faucet, and we know that the mass of that water builds up to a point where the cohesion of the water tension, can no longer hold it to the faucet, and it drips at a very regular rate, which means in this case you have half the glass filled in 1 hour, you have 3/4 of the glass filled in 2 hours, and you have, or maybe that's half the glass in 2 hours, that's probably what it is, and then you have the whole glass filled in 4 hours. So if you look at our radioactive decay, you start out with 100% of the mineral that's the radioactive isotope in half the time that it takes the mineral or whatever radioactive isotope to decay. That's 50% right there. It's going to take 1 half-life, or in this case what we're talking about is that it's 1/2 to the nth. This would be 1/2 to the first power. 2 half-lives would be 1/2 to the second power. That's 2 half-lives, which means you have 25% of the material left after 2 half-lives. Why? Because if you take 1/2 times 1/2, that equals 1/4. That's this right here. And 1/4 is 25%. So if you look, 1/4 is 25%, because if you take 4 and you divide it into 1, it takes 2. 2 times 4 is 8. That's not going to be enough room for me. Just a second. I'll give myself more space. I want you guys to think about this. So 1/4 is equal to 25%, which is, if you look, that's what they have right here. But the reason it works out that way is if you take 4 and obviously divide it long division, that's going to be a 2, gives us an 8. We subtract this, that's 2, that's a 20. That turns that into a 5. That's the point right there. If you take 0.25, and in order to turn it into percent, you multiply by 100. This is going to equal 25%. That's the basic mathematics of it. But what you're saying is there's 25% left of the original radioactive isotope after 2 half-lives, which means there is 75% of the daughter element that is there, because it can only add up to 100%. Now, because of this, we can get some sources of uncertainty. And the uncertainty comes in for, this is basically how we date rocks. In this case, we have magma. Certain crystals will incorporate specific densities of parent atoms, and there are stable daughter atoms that are already there. But then once they're crystallized, we know that we can then look at these crystals that started out as parent atoms and look at the half-lives of the daughter nuclei to the parent, the ratio there. And so there are certain things that we need, certain properties of this rock in order to be a good specimen. That is, it's an unweathered, fresh specimen. Most sedimentary rocks cannot be dated with these methods because we're using other methods like the stratigraphy. We can also date fossils. We can use other radioactive isotopes. We don't use the minerals. But anyway, we can use, as long as there's not any kind of weird metamorphic event or something going on, we can get a pretty good idea of what the rocks look like or how old the rocks are. What happens is sometimes you'll get the situation where the igneous rock, you get the crystals formed, you go through metamorphism, and because we know that the metamorphic change causes crystals to realign and move and migrate through rock, the daughter nuclei can migrate out, and a rock that we normally think like this, or a crystal, excuse me, that we would expect to be 700 million years old when we start looking at the half-lives, is actually 350 million years old because the daughter nuclei has already migrated out, because we're looking at a ratio. In this case, this would be 100%, and then we know after so many half-lives we have, 1/4 or 1/8 of the material left, and it would normally be, let's say it's 1/8 in this case, because we've already had 1/8 at one point, and we actually squeezed out, I'm putting in quotes in my head, squeezed out the daughter nuclei, which made it look like it was 700 million year old rock, when in reality it's only 350 million year old rock, because it's already gone through radioactive decay, and you've realigned or changed the crystals. And that's one source. That's a problem when we're looking at using radioactive decay to get the age of rocks. Here are some radioactive isotopes that we use, their half-lives, and then the the absolute ages that we can look at to determine, certain things, like we use potassium that decays into argon, but we can look at 100,000 to 4.6 billion years old in the different rocks. Of course, we talk about radiocarbon dating in a second, but we also can use uranium, which goes from 10 million to 4.6 billion. And then, of course, this whole group right here, which can be used to look at rocks from 10 million to 4.6 billion years old to get their ages. The reason we don't have a lot of the rocks that are older than 3 billion years old is because there just aren't a lot of those rocks around. They've gone away. They've gone through the whole rock cycle, and they've become igneous again. Here we also can look at fission tracking, which is where they break down and they scar the rock, and we can actually just count those scars to determine how old they are. And then, of course, just like I said, we can use absolute dating methods for carbon-14, and that's where we use the half-life of carbon-14, which is about 5,700, not about, it is 5,730 years old, or years for one half-life. And we know that cosmic rays come down and hit nitrogen, which then turns the nitrogen to carbon-14, because it's a neutron capture, which changes the type of element without changing its mass. And then when animals are eating food and the plants take in the carbon-14, they don't care if it's carbon-14 or carbon-12, or carbon-13 or carbon-12, they just take it in. And then the animals eat this material that fixed carbon from the atmosphere, which would be the plants. And then those animals die, which means they're no longer taking in carbon-14, which means we can use the half-life to figure out how old these animals were, how long ago they died. Really, it's not how old they were, but how long ago they died, because they're no longer taking in carbon-14. Now, we can go up to about 70,000 years with a lot of this organic matter, because, after you get out of half-lives up to, something like to the 12th power, that's not very much stuff left, because this would be 1/2 multiplied 12 times. It gets very small amount of original material left, in this case carbon-14, so it's very hard to identify the ages after about 70,000 years, which means we can switch to other things, like we talked about potassium. We can go up to 100,000 years. The problem is potassium is contained in the water, where it's harder to know if that's the original potassium in the organism or if it was actually moved in by the groundwater. So that's why we tend not to use potassium unless we are sure of the source of that potassium, the radioactive potassium. We also do dendrochronology, which is, we do this in environmental science, where we go out and we core trees and we reconstruct the past in Michigan based upon these tree cores. And we know that there's a white oak that we have on campus in our forest that is older than 500 years old. It's a swamp white oak, which means, think about it, that's a pre-Columbian tree. That means before Columbus discovered America, that tree was growing as a little sapling. And we can actually use, we're not going to cut it down, but we could use the tree rings. Once it dies, we know the age. We can go all the way back and reconstruct the history of Michigan, 500 years. It's pretty powerful if we want to look at, global climate change or any of that kind of interesting changes or things that are going to impact us in such a way. So what do we do to develop a geological timescale with absolute dating methods? Is we look at the radioactive isotopes and we reconstruct it based upon those radioactive isotopes. We usually will say, okay, here's a metamorphosed rock at 750 million years old. We know that there's an ash here that's 675 million years old, and then another lava flow that's 600 million years old, which means we can look at then the layers sandwiched in between and get a pretty good idea that these are 675 to 750 million years old, and then you can count the layers and actually find all the different layers down to a million years, in divide, or you can even go 100,000 years depending on how good the layers are. So the absolute ages of most sedimentary rocks are determined either by fossils or they're established indirectly by looking at the igneous rock and getting the absolute dates and then counting up the different layers and figuring it out that way using old-fashioned sleuthing, so to speak. So the first thing we do is we can use absolute dating, and then we use stratigraphy, which are the layers, and we use stratigraphic terminology to determine. So if we are in the Mission Canyon Formation, that's a type of rock, or the Lodgepole Formation, we know that they've been dated to a specific age, we know what they look like, and based upon their lithology and any of the fossils that are, we can get their related geological time based on the next, it's a slide after this, but we have, or 2 slides later, I think. So we start putting these different stratigraphic groups into different ages or eras or eons, depending on, very large supergroups to very small groups or beds in this case. So here we have the supergroup, which is, it's kind of weird, it keeps on picking up the pictures. We have an eon, we have the era, which is the unithum, the erithum, the system, the series, and the stage, or in time units, it's eon, era, period, epoch, and age. And then, of course, the lithostratigraphic units are the supergroup, the group, the formation, the member, and the bed. We talk about bedding planes. You've heard me say that. And that's basically, the bedding plane is the age or the stage. So we have the lithostratigraphic groups are defined by the rock type or the assemblage of rock types that are there, which are the basic units of formation, and that's mappable within, meaning we can distinct upper and lower boundaries. We also have the biostratigraphic units, which are recognized on the basis of fossil content. We use that with the lithostratigraphic. And then the time stratigraphic, which are consistent with the intervals of geological time. Either there's some igneous rocks there or something we can put it in. And then there's the time units, which are, these things that we already use in the geological record, which are, eon, era, etc. So these all can be correlated, and they're correlated by looking at, we have a stratigraphic section here, we have a biostratigraphic, and then radiometric dates. And based upon all these different types of data, we can come up with some very specific ages for the sandstones or whatever's in between. We can actually sandwich this stuff. We get, within, here we got 200,000 year difference between these two groups, right? We can get it down to very, very small numbers and figuring out the ages of the different rocks, and we just then correlate them. So here you have 160 million years down to 0 million. It's actually on the bottom here the way they've done that, but if you were starting at the bottom and going all the way up, there's 160 million years contained within this, the Bear Paw Formation, which is, I think another formation, was it in this one? I don't think it's in the Montana one. There's also other ways besides looking at specifically these radioactive isotopes of carbon or rock layers. We can actually look at the dripstone, and we know that certain things get covered in the dripstone, the stalagmite or stalactite, stalagmites we usually use, and the layers are formed just like layers of trees. And then we compare the different dripstone layers, and we can look at, uranium-234, which decays into thorium-230, and each layer of the growing stalagmite can be dated to a specific time period. Excuse me. Another method that I don't think is in your book, this is a picture that used to be in your book, and we basically use radioactive oxygen to look at global climate change, because at different temperatures there's different concentrations of oxygen-18 in plants and other organisms, and it's directly related. Here we see it's directly related to the temperature. The higher the temperature gets, you have more or less oxygen-18 over oxygen-16, because oxygen-16 evaporates easier or vaporizes easier than oxygen-18 because of the density difference. And so water pools, the stuff that the plants pick up and everything else, are oxygen 18 rich under higher temperatures. And then of course we can look at layers in the stalagmites using a core just like we do in the trees, and we can look at the climate conditions in the past based upon the different oxygen 18 or oxygen 16 that's in the stalagmites. So in this chapter we talked about the relative dating of geological layers. We talked about how we correlate those rock layers through consistency of different structures, fossils, and lateral um, uh, consistency, basically. And then we have the absolute dating geological layers using radiometric methods. And then we put all those different ideas together to build the geological record and geological time. And one thing I want to note is there's a lot of comments that I get over the years when I've been teaching this about gaps in the fossil record and how that throws a ball of wax into it, and it's not true. The fact is the Earth is very large, and I'm sure there are areas where very old rocks just have eroded away. They're just not around anymore. They're probably somewhere on the Earth, but they're covered up by newer rock. I mean, there's a gap in the Silurian that we are aware of. We just haven't found rocks from that time period. So we just don't find fossils. We don't have rocks that are that age group. So these gaps are just to be understood as we just don't have a complete record. We have a really good record. There are a few gaps, but it doesn't negate the fact. It's like I ask students all the time, were you present at your birth? Well, can you describe it? Do you remember it? Obviously you don't, but it doesn't mean that it didn't happen, right? There's a gap in your memory. It's kind of a silly one, but that's a very prevalent one for most people because I believe we've all been born, if you get the idea. Okay, that pretty much summarizes Chapter 17, and I hope you guys have a good evening or afternoon, depending.